Hey guys, I want to take a moment today to go ahead and talk to you about collisions, and in particular, looking at the math for collisions in the terms of momentum and the law of conservation of momentum. So let's jump right in and take a look at our essential questions. Now, first of all, we need to understand what the law of conservation of momentum is, what it says, and how we can apply that using it as a tool to help us understand what happens in a collision and also an explosion, which we'll talk a little bit more about later. Number two, how do you differentiate between perfectly elastic and perfectly inelastic collisions? Okay, what separates these two concepts together, both in terms of what we see, hear, feel, and in terms of the math, so we can calculate them? Number three, where do most collisions fall in the spectrum between perfectly elastic and perfectly inelastic? And then lastly, how does an explosion relate to collisions and our ability to calculate their momentum and energy? So let's review some key things. We talked a lot about momentum and impulse already. So let's go ahead and refresh our minds in terms of how those two quantities work and are related to each other. Firstly, we talked about this idea of momentum being mass in motion. It's mathematically written P equals mv, or momentum equals mass times velocity. So you can have a large object moving slowly or a small object moving very quickly, and they can have the same momentum, but they have to be moving in order for that to work. When we start looking at impulse, impulse is the amount of force per time. Okay. And so when we go ahead and look at this, we typically relate this to the change in momentum. And so when we take a look at this, let's look at the math for this really quickly. So if we were to take a look, we talked a lot about this idea of momentum equals mass times velocity, and impulse, I'll just say impulse, is equal to force times time. And when we go ahead and use Newton's second law to help relate these to each other, what we end up seeing is that mass times a change in velocity is equal to the force times change in time. And so this is the relationship that we have between momentum and impulse. And this is what we've been using now for a little while. So we want to go into a little bit more detail and expand that outward to give us a better understanding of momentum. And last class, we talked about this idea of momentum before and momentum after, and how those two are related to each other in terms of any situation. Now, if we assume that we have a closed system, and if you remember, we talked about this idea of system versus surroundings, okay? Everything contained within a certain area is the system. Anything outside of that is the surroundings. For this to work, okay, for this to work, we need to go ahead and be dealing just with what's inside the system, and then we can have momentum before equal to momentum after. Okay, and mathematically, we typically write this out as momentum final is equal to momentum initial, or vice versa. So you can't change or lose it, just like the law of conservation of mass or the law of conservation of energy. So in a closed system, the momentum before a collision is the same as the momentum after a collision. Now, it doesn't work perfectly that way. We have to actually keep in mind this idea of energy conversions that we talked about, because in an energy conversion, you can see some of that kinetic energy of movement be converted in the collision to sound, to light, to deformation of the bodies in the collision. But if we can quantify all those, we can go ahead and say that yes, the energy in that particular collision is conserved. And so when we start looking at definitions for whether we have a perfectly elastic or perfectly inelastic collision, we have to keep in mind this idea of energy as well. Okay, so the conservation of momentum is a fundamental concept in physics, right up there with energy and mass that we've been talking about. And it states that within a given isolated system, remember system versus surroundings, the amount of momentum remains constant. Therefore, momentum is neither created, nor changed, nor destroyed, according to Newton's laws of motion. So, dealing with momentum is a little bit more difficult than dealing with mass and energy. And the reason for this is because momentum, because it has velocity in it, is a vector. Okay. And vector quantities have both a magnitude and a direction. And so we have to go ahead and think about the system before the collision, including all those different vectors, and the system after the collision and all those different vectors. Momentum has to be conserved in all three physical dimensions at the same time. And so it's very important when we do more complicated versions of this that we remember how to break out component vectors. That we can take the x and y components out of any vector, and then we can go ahead and add those up more easily than the vectors themselves. Okay. Even in massive cases, when we have a rocket launch, something like this, momentum is conserved. The velocity of the rocket and its payload is determined by the mass and velocity of the gases that are expelled out of the back end of the rocket. This is Newton's third law, action-reaction pairs. Okay, so ultimately we have to remember that in an isolated system, we have no net force, and therefore the momentum before the collision is the same as the momentum after the collision. And we'll talk about this with respect to explosions and stuff as well here, because it's the same thing, this idea of momentum before equal to the momentum after. When we start looking at a collision is when there are two or more particles that are coming together for a very short but intense interaction. And we typically look at this idea of, it being almost instantaneous. Now, it's not. We can think about impulse again, but that's what we kind of think of in terms of most collisions. An explosion is the same sort of thing, but in reverse. Okay, short, intense interaction causing the separation of two particles. Okay, so maybe pieces get blown off during an explosion, that type of thing. So a collision is a short duration interaction. It's not instantaneous in real life because materials are going to give and bend and bow. And so I'm going to go show you a picture here in a second. And this is the collision between a tennis ball and a tennis racket. And when we think about it, we think of it as an almost instantaneous thing where the tennis ball hits the racket and bounces back the opposite direction. But if we look closely, we see that the tennis ball and the tennis racket deform and then go back to their normal size as they go ahead and finish the collision. So it takes time to compress that ball and even more time for the ball to re-expand as it leaves the racket. So let's look at that picture again. So what's happening at an atomic level? So if we looked at it really close, you'd see the vibration of all the particles that make up the matter that we're looking at here. They get super close to each other. They actually interact each other, creating these forces. Again, force pairs. And then what ends up happening is that's going to go ahead and be absorbed by the racket in your arm on one side, and then the ball is going to speed off in the opposite direction on the other. So object A bounces back and the bonds re-expand to their normal shape. Now, in this example, momentum is conserved, like in any other collision. And so this is where we get these terms perfectly elastic or perfectly inelastic. In a perfectly elastic collision, both momentum and kinetic energy are conserved. The closest thing we can probably think of, although it's not a perfect example, is the collision of billiards balls or steel balls of the Newton's cradle. Okay? One hits and it takes that energy and transfers it to the other one. Now, again, that's not perfect because if you can hear them click, some of that energy is being lost in the conversion to sound energy. In an inelastic collision, kinetic energy is not conserved and converted into other forms of light, such as heat, sound, or work to permanently deform an object. And when this happens, perfectly inelastic collisions occur when the objects stick together. So not all of the kinetic energy is necessarily lost, and so the two combine and move off. And if we assume that there's no kinetic energy lost and there's no energy transformation, then we can see the two objects moving off together, and we'll look at that here in mathematical format here in a second. But in all actuality, most collisions fall somewhere between elastic and completely inelastic collisions. Okay, they lose some energy, they may stick for a little bit, but then they drift apart. So we're looking again kind of at more ideal conditions. And so that's just something to kind of keep in mind as we move forward. So again, in an elastic collision, both momentum and kinetic energy are conserved. And in an inelastic collision, momentum is conserved, but kinetic energy is not. And so our calculations are going to be done based on momentum. Okay. In a perfectly inelastic collision, momentum is conserved, kinetic energy is not, and the two objects stick together after the collision, so their final velocities are the same. Well, let's think a little bit about this. In terms of a collision, in terms of trying to absorb force, because that's really what we're doing, if you're in a car accident, why do airbags work? Well, airbags work because it increases the time of the collision. So increased time of collision decreases the amount of force because that change in momentum is equal to the impulse that we talked about before. It spreads out the area of contact as well, which is going to decrease the pressure and prevent the potential for any penetrating wounds, we hope. Okay. But in either case, we're still dealing with this concept of the total momentum after the collision is equal to the total momentum before the collision. This is the equation that we typically use. Okay. I actually typically will use the numbers 1 and 2 instead of A and B, but it's the same concept. Okay. The mass of object 1 or object A here times the velocity of object 1 or object A initial before the collision plus that of object 2 is equal to that of object 1 and object two's momentum after the collision. Okay, so again, in order for this to be true in a closed system, momentum before the collision is equal to momentum after collision. And you can see in this example here that as block A, which is smaller than block B, comes at block B, it has a certain amount of momentum. Block B, as it speeds towards block A, is a little larger and it has a certain amount of momentum. When they finish the collision, okay, then we have to say that if this is a true collision, that they're going to have the same momentum afterwards. But vectors become so important. Okay, what is the net momentum before? What is the net momentum afterward? And you can see that in real car accidents, it doesn't usually happen in a nice, smooth, even plane. And so now you have to deal with the same thing, but by using our sine, cosine to get the X and Y components, we can go into 3 dimensions. And this is actually one of the techniques used by a lot of forensic scientists that work in with insurance companies and police officers as they try and do forensics on a car crash to see who had the most speed coming in, where they were coming from, based on where the cars end up. And this is a big reason why they don't want you to move your car after the accident until the police get photos of the site so that they can go ahead and kind of predict or walk through what happened in the accident. So here are your collision equations. We have our elastic and inelastic. Notice that in the elastic they separate. So you have a different final velocity for object 1 and a different final velocity for object 2. In the inelastic collision equation, you'll notice that they are added together and you have a single final velocity because they stick together. And so therefore they have the same final velocity. But you can also do this in reverse. When we break them apart, objects are combined together with a single starting velocity and ending with separate velocities. This is the equation that we would use for an explosion. Okay, starting out as one object, and then it explodes outward. We track the different pieces that came off of it, and we can go ahead and use this equation for explosion. So maybe we should go ahead and label it as such if you haven't already. This is the equation for explosions. Okay, because they start together and they finish apart, which is the opposite of what we did for inelastic collisions. They start apart and they finish together. Okay, so keep that in mind as you go ahead and move forward. All right, so let's take a look at an example. Most of your collisions are not going to be contained within just a single dimension. So we typically have to skip up to 2 dimensions or 3 dimensions. But the law of conservation of momentum still applies. And this is where those vectors become even more important. Okay. If you have the collision of these two objects you see here, two particles, let's say, one has momentum coming in, the other one's stationary. When they hit each other, think about it like pool balls, right? When they collide with each other, they both end up moving on, but it changes the direction of the two objects in terms of the direction they're going. But we can calculate this out by finding the x and y components of the final velocities. And we do this by using sine and cosine to go ahead and identify those component vectors. A great example of this would be something like this car accident situation here, because we have the initial velocities. And if I were to go ahead and give you the masses of the two cars, we could go ahead and take a look at this idea that they have their initial momentum coming in. One's all vertical, the other's all horizontal. And then after the collision, if we assume their front ends stick together and slide together, we can do this as an inelastic collision, and we can go ahead and look at the angle that they go off the main and take a look at the x and y components to make sure that they balance out with what's coming in, so that momentum before equals momentum afterwards. So one of the best things you can do when you're doing this, and I know I've been saying this all along, is to go ahead and do a drawing. Okay, make a diagram, okay, so that you can see what's happening visually and make sure that your vertical and horizontal components, especially since you're going to have positives and negatives, balance out. Okay. Ultimately, once you've done that, nothing is any different than a very simple example. We just have to do it more often to get the different vertical and horizontal components. Okay. So let's take a look at this. Let's say we had our initial momentum from object one, and that's going to the right. And the initial momentum for the second one is nothing. There is no line because there is no motion. Then we go ahead and take a look at the initial or the final momentum for object 2, as well as the final momentum for object 1. We can then go ahead and add those two together by going ahead and doing component vectors. So there's object 2's final vertical and final horizontal. We can also look at the horizontal and vertical for momentum for object 1 final. If you were to go ahead and add these together, what you would notice is that the vertical components, since this came in perfectly horizontal, would cancel each other out. Okay, one went down, one went up, but those two pieces would cancel each other out. And then what you end up with is you end up with this horizontal component that matches, okay, some of the momentum that we saw before, but some of it was lost in the diversion of the pathways. Okay, we can determine that using those angles. Now remember that an explosion can be calculated the same way as we do a collision. We just take that inelastic collision equation and reverse it. The particles first start together, then they have a brief intense interaction, they explode apart, and as they do, we have to remember that the law of conservation of momentum says that the momentum before the explosion is the same as the momentum afterwards. And so as far as one piece goes in one direction, another piece has to go in the opposite direction to cancel that out so that we have an F net of 0. Okay, so total momentum will still be conserved. So think about that when we start watching fireworks as we get to that this summer. All right. This figure shows a rocket with a parcel of fuel on board. And so if we choose the rocket and the gases to be the system, the burning and expulsion are both internal forces. And the exhaust gas gains backward momentum as they are shot out the back. And the total momentum of the system has to remain 0, so that means there has to be momentum of the rocket being moved forward. This is those force pairs we talked about in Newton's third law. So the rocket gains forward momentum by the expulsion of the ejected exhaust gases out the back end of it. All right, so let's do some practice problems. Okay. We'll give you this one and we'll go over it together, but we want you to get a chance to go ahead and try it. So find yourself a sheet of paper and something to write with, preferably a pencil, not a pen. And let's go ahead and take a look at a recoil. Now, how many of you fired a gun before, especially something like a rifle? Maybe you've done a shotgun. Okay. Let's say we have a 10-gram bullet and it's fired from a 3-kilogram rifle with a speed of 500 meters per second. We want to know what is the recoil speed of that rifle. Okay, so they start out together. First thing we should do is go ahead and do a drawing. This one has one already for you. Okay, the figure below is a pictorial. You can see your gun here starts out with 0, okay, meters per second. And you take a look at your bullet, and it has 0 meters per second. We've converted the 10 grams into 0.01 kilograms, so we have the same units. And then we can go ahead and calculate this out. Okay, we take a look at the overall system, MV1, MV2, both of them initial are 0, so we have a net of 0. Now, once we fire it, however, it does not stay that way. Now we have the bullet flying at 500 meters per second, so we need to solve for what is the final velocity of the rifle as it kicks back. Okay, now hopefully you recognize, because they're in opposite directions, one of those is going to have a negative sign on it. Now, we would probably go ahead and assume that the 500 meters per second is positive. And the reason for that is that's the direction the bullet's supposed to come out. And in this case, as the drawing has been set up, we typically use the right direction as positive. All right, so then what do we do? Well, now, in order to calculate this out, we have to remember all of the things I just mentioned. And if we assume the friction is minimal and we can go ahead and generalize this, you should be able to go ahead and calculate what this would be. So I'm going to take this off and take a minute, pause the video here, go ahead and try doing this calculation, and then we'll come back and go over it here in a second. Okay, so hopefully you've had a chance to try it and give it a solve it. Now let's go ahead and see what you did. Okay. All right. So if we go ahead and take a look at this picture, okay, let's go ahead and deal with our constants. Okay. We have M1. We'll say M1 is that of the bullet, and that's equal to 0.010 kilograms. And we have mass 2, and that's equal to 3.0 kilograms. We've got V1 initial, 0 meters per second. V2 initial equal to 0 meters per second. We've got which one did we say was M1? Okay, so V1 final is equal to 500 meters per second. and we're trying to solve for V2 final. Okay, so let's go ahead and put up a screen. There we go. So those are the numbers that we have. We have our drawing that we saw here in a second. Now we need to go ahead and set it up in terms of our equation. So we're going to use this as M1 V1 initial plus M2 V2 initial equals M1 M1 V1 final plus M2 V2 final. Now let's plug in what we've got. So the first mass is 0.01 kilograms, and its initial velocity is 0 meters per second. Plus, we've got the 3.0 kilogram rifle times its initial velocity, which is also 0. This equals, again, 0.01 kilograms. That's that rifle bullet, and that's now traveling at 500 meters per second. And we want to go ahead and add that up to the 3.0 kilograms times V2 final, which is what we're solving for. So, well, this equals 0 kilogram meters per second plus 0 kilogram meters per second equals, and that's going to equal 5 kilogram meters per second plus 3.0 kilograms V2 final. Those combine 0 kilogram meters per second plus 5 kilogram meters per second plus 3.0 kilograms V2 final. We'll subtract this to the other side, minus 5 kilogram meters per second equals 3.0 kilograms V2 final. Divide both sides by 3 kilograms. And we end up with negative 5/3. And the kilograms are going to cancel here. And that leaves us with meters per second equals V2 final. So that's what, 1.6 repeating. So negative 1.6 repeating meters per second equals V2 final. Okay, and so notice that minus, that's important. That negative tells us that it's going the opposite direction. If the bullet's going to the right, then the gun is going to the left, which is perfect for a recoil. Okay, so great work. I hope that went well for you. Let's go ahead and try another practice problem. A 1967 Corvette of mass 1450 kilograms moving with a velocity of 100 miles per hour, which is equal to 44.7 meters per second, slides on a slick street and collides with a Hummer of a mass 3250 kilograms, which is parked on the side of the street. The two vehicles interlock and slide off together. What is the speed of the two vehicles immediately after they join? So pause the video here. Go ahead and solve this problem, and then we'll go over how to do it. Okay, so welcome back. So let's start out with our knowns. Okay, so let's start out with the mass of the, let's see, what do we have? Corvette, and that's going to be 1450 kilograms. We have the mass of the Humvee, which is going to be 3250 kilograms. We have our velocity initial, VCI, velocity of Corvette initial is 44.7 meters per second. And we have the velocity of the Humvee initial, 0 meters per second. So what we want to know is what is the velocity final for the two combined afterwards. And it's important to note that it says that the vehicles interlock. So in this point, they are going to go ahead and join together. So we have MC VCI plus MHVHI I equals parentheses MC plus MH V final. And this is what we're trying to solve here. So we can go ahead and know that this is 0. So this one we can kind of ignore here because it has 0 initial velocity. And so what we're really starting with is the 1450 of the Corvette plus its initial velocity, 44.7 meters per second. And that will equal the combined, got our 1450 plus 3250 kilograms from both, times V final. Okay, so now let's go ahead and simplify that. And when we add those, we'll multiply these two together. I get 64,815 kilogram meters per second. That equals, we add these together, and we get 4,700 kilograms times V final. Okay. Then we divide both sides by 4,700. And what we get is I get V final equals 13.7 meters per second. Well, let's do 8.8 meters per second. It's 7.9, so it rounds up. Okay. And that's what we're going to go ahead and take a look at. All right. So hopefully you were able to get that as well. 13.8 meters per second. Let's go ahead and try another one. We've got a 58, 79 pound or 2665 kilograms, use the kilogram number, Cadillac Escalade going 35 miles per hour. And it smashes into a 2342 pound or 1061 kilogram Honda Civic moving at 35 miles per hour. Also, this is 15.64 meters per second in the opposite direction. So they're coming head on into each other. The two cars collide and stick. What is the final velocity of the two vehicles? So pause the video here, go ahead and solve this problem, and then we'll go over the answer. Okay, so what'd you get? I got 6.73 meters per second, which converts to 15.1 miles per hour. I hope you got that. If you didn't, please go ahead and talk to me and we can go ahead and go over it together. All right, so now let's go ahead and look at a different one. In this case, instead of car collision, let's look at a baseball bat. Pitcher throws a 0.145 kilogram baseball, so it crosses home plate horizontally with a speed of 40 meters per second. It's hit straight back at the pitcher with a final speed of 50 meters per second. What is the impulse delivered to the ball? And find the average force exerted by the bat on the ball if the two are in contact for 2.0 times 10 to the negative third seconds. And what is the acceleration experienced by the ball? Okay, so here you'll have to go ahead and do your change in momentum. And then you'll go ahead and have to relate that back to impulse that we talked about last class to go ahead and solve the three parts of this equation. So go ahead and take a look at that. Do your practice, solve these problems, and then let's go ahead and go over it. Pause the video here and go ahead and try your math. Okay, what'd you get? So for me, I got 13.05 kilogram meters per second for my change in momentum, which remember is the same thing as your impulse. We just change the units typically. I guess I didn't hear, but that would end up being Newton meters. Okay, Newton seconds, excuse me, Newton seconds. And then when we go ahead and take that, we can find the force by dividing by the time, which is going to give us the 6,525 newtons. And the acceleration, once you have the force, you divide that by the mass, and you can go ahead and get the acceleration. So pretty cool now that we're able to use all these different tools together. So I hope you guys are appreciating this and enjoying it. All right, last thing. James Clerk Maxwell once walked into a pool hall to observe a game of billiards. Okay, He remarked that he knew with certainty, without making any measurements, that the collisions between the billiard balls were inelastic. How did he know this? We talked about this earlier in the game and earlier in the notes. All right, so I'll leave you with that. If you have any questions or if you're unsure why, please go ahead and talk to me. All right, guys, stay healthy, stay safe. I'll talk to you soon. Take care. Bye bye.